record and share my screen. And so we have one last week of material to cover. And this material is sort of totally separate from the other material that we've talked about in the class so far. And so that's why it's coming at the end of the course here and after the final, and stuff that only the non-graduating students have to complete. So the two keywords that are related to what we're talking about, coroutines and asynchronous programming or async programming. And the idea of this topic is that there's a lot of functions in Python in particular, but every programming language in general, that do like input, output, IO operations. And these functions are slow. And they're slow because they're what we call blocking functions. They don't do anything while we're waiting for the IO to happen. So in the context of the search engine, if we had a web crawler going out and accessing web pages, if we have a really slow web page that we're trying to access that takes 30 seconds every time we're trying to access a page, with normal Python operations, then we can only access one page every 30 seconds. So really, really slow. But the idea of coroutines, async programming, is that we'll be able to get this faster. So network access, one of these sort of main operations are examples of IO, but also reading from a file, something that can be slow. So yeah, traditionally, again, if we have our CPU, it's these blue boxes down here, and we're doing some sort of computation, and then we have this function call that does this IO operation, read from the disk, read from the network. Then we're waiting for the IO to do its thing, the CPU is not doing anything, and go back to the CPU once that's done, and it's just going back and forth, and there's no overlap between what the IO is doing and the CPU is doing. And this is just all Python programming that we've seen so far is all structured this way. The solution to this is asynchronous programming, so async, short for asynchronous. And here, all these IO calls overlap each other, and they also overlap with the CPU processing. And so something that took a long time up here, shortened down quite a bit down here. And so it's obviously a lot faster if we can do all of these things, all these IO operations concurrently, but it's going to make our programming a little bit more complicated. There are a lot of techniques for doing this asynchronous programming, threads, callbacks, promises, and many more. But the particular technique that is sort of the most popular one these days, especially in the Python world, is coroutines. And so that's what we'll be talking about. Coroutines in Python use this special async await syntax. And so async is often just synonymous with coroutines. Async can be a little bit more general, referring to any method for asynchronous stuff, but in the Python world, async, because that's a keyword in Python, is specific to coroutines. The origin of the word coroutine, so routine is like a synonym for function, and the co is like cooperative, so a coroutine is a function that's going to cooperate with another function. Again, the most popular technique for doing this in Python right now, computationally particularly efficient, better than all these other solutions in Python at least. And have easy here in scare quotes, easy compared to other techniques, but still not in any absolute sense easy. We'll see that it's relatively weird. I'll cover the syntax here in just a minute. We'll switch to the terminal and talk about the history as we do that. And actually, while I'm doing that, I'll mention there's a number of Python files that we'll be going through, these up here. And so if you wanted to follow along, these would be the files to make sure that you have on the Lambda server to follow along with. But I'll talk about the history of the development of this syntax as we talk about those, and jump over to the applications real quick. So we've talked about web frameworks in general so far. We've seen a long time ago WSGI with so Django's what Instagram's using. Flask is the more popular one these days. both of these, or all of these, are using this Python web server gateway interface defined first in 2003. ASCII has not totally replaced it, but is sort of the up-and-coming contender. And so these PEPs are Python enhancement proposals, things that are like personally signed off by Guido van Rossum that like, yes, I want this in the Python language. So this is when that was signed off on. ASCII, not signed off like that yet, no official stamp of approval. It's just sitting in a GitHub repo. This Fast API framework for developing websites is sort of the flagship framework for ASCII. First started in 2018, so much more recent than these other ones. And if we take a look at this performance comparison, I think I have it right here. Let's zoom that in a little bit. If you're looking at the number of responses that we can do per second on just standard hardware, the Fast API is going significantly faster than all the other frameworks. So bigger is better, more requests per second. So 13,000 versus say like 1,000 for standard Flask. And that's because of this asynchronous sort of techniques that allows it to really maximize your CPU usage. Besides the web frameworks, so database access, we've been doing a lot of that in Python. SQL Alchemy, the library that we've been using, just in this latest version, 1.4, introduced beta support for these asynchronous operations. So it's beta. They don't recommend people use it because their interface is likely to change. PsychoPG3, you may have seen in like the error messages that you've been getting from SQL Alchemy. They've been saying PsychoPG2 in them sometimes, because that is the PG2 is the version of the library that SQL Alchemy is still based on. Version 3, which is just released this year, actually introduced async support in a stable way. So there's all like very new cutting edge sort of things being added into Python and the Python ecosystem. And yeah, I'd say the takeaway about like this high level introduction is that all this async stuff is going to make your code fast, especially IO code, so disk reads, network operations. And not everything is async yet, but I don't know, in 10 years, say, everything will be async in Python. So now is the time to get on the async bandwagon and learn how to use it. So that we're going to jump over to the syntax. We'll spend the rest of today getting a feel for how async functions work under the hood. And then Wednesday will be our last day of class. We'll talk about how to actually sort of use them and practice for your last homework assignments. Yeah, so there's two references for today. I won't link to them, but if you want like a more detailed explanations of things, those are the references to look at. Async is the sort of thing that it just takes seeing multiple different explanations from multiple different angles to really understand what's going on. That it is basically everybody finds it super weird the first time you see it. Okay, so in the terminal over here, I'm in my week 15 folder. So I have all of those number Python files in the repo. And each one is building up more and more complicated functionality related to this async functionality. And we're going to start, the first few ones are things that at least people who took data structures with me will have seen before relating to generators. And then we'll see how this async functionality builds off of generators. But actually, even before generators, we're going to look at just plain old functions in Python. So this very first, I'm going to do Python 3-i for interactive mode. So I have an interactive terminal down here. This first example function right here, if I just run it like that, gives us our example function. In Python, every function is really just a class, though, that happens to implement this call function. And so this def is just the way to think about it, the right way to think about it, is that it's syntactic sugar for a class which implements the call method. And so this up here, example function, calling that function, is the same as defining an instance of this class and then calling that instance of the class. So like this, it defines this example function2 class, and calling that prints out example function, calls this double underscore call. This double underscore method is in Python world, something like this is called a double underscore method, but nobody likes saying double underscore because that's just takes too long to say. So people who like The Office will call it a dunder method, like Dunder Mifflin, and other people will call it a magic method because it does a lot of things behind the scenes like magic. And in particular, in this case, anytime you have parentheses that you attach to something, what Python does is it looks for the call member of that particular object and runs that member. If we look up here at this example function, if I do example function like this, we'll see that it has the call method implemented, call like that, and that actually runs the function. So really, that is just sort of syntactic sugar for calling the call function explicitly. But yeah, nothing necessarily too surprising about the function definitions with DEF like this. Things will get a little bit weirder when we get to the generators next. So the next file, number 2, maybe it's number 1. Yeah, 01 sugar generators. Oops. And I don't want to open it in Vim. I want to do Python 3-i. There we go. And so here I have a function, factorial list, and this function is sort of the standard way of computing a factorial. If I type down here factorial list 10, then I'm going to get the first 10 factorial numbers. So just 1, then 1 times 2, then times 3, then times 4, and so on, up until the numbers get very large very quickly. The problem with this implementation is that it uses both linear time and linear space. And the idea of a generator is that we'll be able to take away this linear space. If I was just looping over this function, doing something like this, where I only need access to one of these values at a time, then there's no reason to store that entire list as an intermediate thing. So this right here is storing it as a list, and so it's using linear space. The generator of this version of this function uses the yield keyword instead of the return keyword. And what's weird about the yield keyword is that the function sort of stops and restarts. And so that's very different than most functions that we're used to in programming languages. If I call the factorial generator with 10 like this, you'll see that it doesn't actually give me the numbers. It gives me this generator object. In order to actually sort of view these numbers, get inside this generator object, I would use this for loop. Same syntax as I had above for the list version, looping over it. And now it prints out those numbers just the same. So here, this yield, the very first time through this for loop, it's like running this yield, and it gives me the 1. Then it realizes that it needs to run it again, starting from where it left off, and then it'll give me the 2, and then the 6, and then 24, 120, and so on. Each time the yield giving me the next value that it's supposed to give. So this yield, really the way to understand yield is to see like what is it syntactic sugar for. Looking at the syntactic sugar of the functions is kind of, I don't know, just by itself, like a little bit trivial. It doesn't really help us in our understanding. But looking at the syntactic sugar of a generator, I think really does help our understanding. And the only thing that makes this a generator is the fact that somewhere in this function, the yield word appeared. And so scrolling down a little bit more, this is how that generator desugars. This is how this single function right here with a yield inside of it, so a generator desugars. It desugars into two classes, one class representing the function and another class representing an iterator of the function. The main purpose of this sort of outer function is that it has this iter function inside of it, which returns this second function. Inside of this second function, all of the member variables, all the attributes of this class are going to be the same as the local variables of our function. So we have an in, the thing that we're returning, an I. Up here we have the in that's being passed in. I guess I called it x here instead of ret, and then the I. And then this next function is what does all of the code up until it hits the yield statement. So all this code right here is the same as this code right here. And if I were to run this piece of code like this, then we'd see we get the same exact output because it's the same exact thing. It's just a desugared version of the yield version of the generator. And then actually anytime in Python we have a for loop, the for loop is syntactic sugar for something that looks like this right here. So the for loop, the very first thing it does, whatever it has inside of this section to the right of the in, it calls the iter function on that to generate the iterator object. So this TMP right here is going to have type of, it's returning the iter function, returning the factorial iter right here. So the TMP is going to have the type of factorial iter, the thing that contained the next function inside of it. Then we have a while true right here. Every time we go through here, we say I equals temp.next. So whatever the next thing is right here, I equals the iterator.next, I equals temp.next. This right here corresponds to this right here. And then the way that the iterator tells us that it's done iterating is it raises this stop iteration right here. So when we're less than or equal to whatever number we're getting to, we raise the stop iteration error. Down here, we trap that iteration error and break out of the while loop. And so this, I'll go ahead and copy it all down here. It's going to give us the same answer. Hopefully I copy this without a mistake. Yep, and there's the same answer. So every for loop just is syntactic sugar for a while loop that uses this this iterator pattern. If we have an iterator, so like this factorial generator right here, do something like iter equals factorial generator 10 like this, then the type of iter is this generator type, and we can directly call the this next function on it. So iter dot do next like that, and it'll give us, it'll run that function up until the yield statement. So up until the first yield at yielded 1, then it'll run again up until 2, the 6, the 24, the 120, and so on. So hopefully this is seeming reviewish from things that you've seen before about generators. This was added into Python, this PEP proposal 255 right here in 2001. And really the motivation for it when it was first added was to be able to represent certain things in constant space instead of linear space. And the most commonly used generator being the range function, this is just a generator in Python. And since it's used so often in Python scripts, they wanted to make sure that it was implemented as efficiently as possible. Let's see, one maybe fun fact about this Python enhancement proposal and just sort of Python in general, its governance structure, is that all of these Python enhancement proposals, again, reviewed by Guido van Rossum, who at the time was the benevolent dictator for life of Python. He has since stepped down. But he had to put his stamp of approval on this, and there was a lot of discussion about what the right syntax for generators should be. A lot of people still think it's very confusing that just by adding the word yield inside of here changes it from a function to a generator without having a different keyword up here. And at the time, Guido said that we're going to define generators by def still, that it's, he has consulted his language designer's intuition, and that tells him that that's the right syntax to use. Turns out, though, that generators started getting more popular for other reasons other than this, and that leads us to our next document here about coroutines. And so let's dump out of Python there, come over here to coroutines. And so this is a few years later, 2005, and in a coroutine, what makes a coroutine different from a generator is here the yield statement is being used, like there's something to the left of the yield statement. We're assigning a value to the result of this yield statement right here. And what that means is that we cannot just, so a generator cannot, it can still send information out of it, but it can also get information into it. And so this, this coroutine function is sort of the simplest example of a coroutine. And this code up here shows us how to use it. The very first time you run a, well, let's see, one of the differences between a coroutine and a generator is that a coroutine is traditionally using this .send method instead of the _next method. Turns out that after this PEP 342, everything that implements the next automatically implements this send method. So there's really no difference between using them. But if you're using the send method, you're sort of implicitly saying that you want to think of your function as a coroutine instead of a generator. And the parameter here that you pass to send is whatever is going to get sort of returned by the yield value right here. So in this loop, we're going to start with I = 0. I is going to be the number of times that this while loop has iterated through. And the value right here is going to be whatever the result of the yield is right here. So the very first time, whenever you first pass a something to the or first call the send, you must always do it with a none. The reason is that when you first do the send, what it does is it will initiate execution of the function at the very beginning. And since there's no yield statement at the very beginning, there's no value that it can take. And so the very first call to send after you instantiate your coroutine must always be none. This. Here I'm getting a 0 out because it does this. And then while true, we get value equals yield I. The yield I right here, I is equal to 0. So it yielded the 0 to me right here, gave me that 0 value. And but now it's waiting for me, if this function is sort of paused, it's waiting for me to send new information to it. So if I do c.send hello like that, this hello will be passed in to this yield statement right here, put in the value, and then we'll print out value equals hello. I will be added 1 to it, and so when we run this, it'll first print the value equals hello, and then that's from this print statement. Next iteration of the while loop, when we hit the yield, it will yield I, that will come out here as the 1. Say hello world right here. We get the 2 for that second iteration of the while loop. We do this again, test just to see a little bit where these values are coming from. So x equals c.send like this. The print statement value equals test, the print coming from here, and the the x right here containing the result of this yield right here. Should be a 3 now, since that's I was previously 2 and we've added 1 to it. So the key idea that makes a coroutine different than a generator is that this yield statement, you're going to be accepting values from a yield. What makes a coroutine different from a generator is you accept values from the yield. And so the outside world can communicate with your function. Any questions about that? Okay, this maximum is another example. That the idea of this maximum is that it's going to just whatever numbers we send to it, it's always going to yield back whatever the biggest number is that we've previously sent to it. Again, we must always, we'll see what happens if we don't initialize it with a none. Something like that. We'll get this error message, type error, saying you can't send a non-none value to a just started generator. So again, a coroutine is just a special type of generator that accepts values through the send. And oops, must type none here. There we go. And now we can do m.send of 2 gives us a 2. M.send of 20 gives us 20. Coming back here, 3. It's always going to give us whatever the biggest one is that we've seen so far. 600. Now that's the biggest. And always staying with the biggest. And the code for doing that is not too bad. Looks just something like this. Again, we have the yield, and there's something to the left of the yield that we're storing and using somehow. So again, 2005, when this idea of a coroutine first made its way into Python. The next file for us to look at is number 3. And here we're going to start talking about actual multitasking. Coroutines have found a handful of applications, but multitasking is, or like this I/O asynchronous computation is by far their most significant application in Python. And so this file does not use concurrency, but it sort of illustrates why we might want to use concurrency and how we would benefit from it. And the subsequent files are going to modify this file. And so in this file, there's 3 functions: this get page function, read from the db function, and this run function. And the idea here is that, so get page, we can imagine it some sort of like crawler downloading something from the internet, some web page. And so just to keep the code simple right here, it's calling time.sleep with 1, wait 1 second, pretending that's how long it took us to download a web page. Here's our simple web page output. And then the reading from the database, very common to another common IO operation here that's divided up into 2 steps. First, getting your connection, and then actually getting the data right here. And then the run function, just calling both of those 2 things synchronously, one after the other. And you'll see that it just adds up their total runtime together. So nothing particularly amazing here, but just this idea of we have these 2 tasks that we wish that they could run at the same time, because they're not really doing any CPU load, just using 2 different external resources. And so how can we make them both run at the same time? And so we're going to modify both of these 2 functions using this coroutine syntax to make that work. And that'll take us to the multitasking 2 file right here. Control D, up arrow. 04 multitasking 2. And so here I'm going to just zip back and forth between multitasking and multitasking 2 to just highlight some of the differences real quick. The print statements all stay the same. Here, this call to time.sleep, you'll notice that it's going to have a yield come in front of it, and this return is going to be replaced by a yield. So anytime where there is an IO operation happening, we will use a yield right there. That yield will say that our function doesn't need to be working anymore. We can go back to the main program to operate. And anytime we actually have some data that we need to sort of actually return, then the yield will be able to do that for us as well. Here, this yield, when it's not returning data, but returning sort of representing the IO operation, it's actually a tuple, a two-tuple. The first one sort of representing what the IO operation is, and the second one being a time of how long we expect that IO operation to take. And so let's just dump back and forth, and you can see those same changes. Those are the only 2 lines that changed, and again, yielding all the IO operations and yielding the results of the function. 3db function goes similar. That's just all the IO operations replaced by yields, and the return also replaced by yield. What's going to be different, though, is that now we'll have a scheduler program that will go through and sort of manage this, this get page and this read DB function calls. The scheduler is going to be keeping track of which is the next IO operation that we expect to finish and call that particular generator once it's ready to run, once it's done doing its IO. And the details of that are, well, there's a lot there. So the details of that aren't super important, but the idea is that it's just keeping track of which is the next IO operation that's going to be ready for us to actually proceed with. So in this case, we can start the download, start retrieving from the database at basically the same time. But then this IO operation right here is going to happen much quicker than this one, and so we'll be connected to the database before we're done downloading the page. In order to run this, to try it out, so this scheduler takes a list of coroutines as inputs. So scheduler, list, and so get page, read db, like that. And this is doing the same, all the same work, calling the same functions as our previous multitasking was, but now it is actually sort of interleaving those operations. We can see it started to download the page, retrieve from the database, and then it's able to connect to the database. Then it downloads the page, gets the information, and then it's done retrieving the data from the database. So it interleaves those in the optimal order. And because of that, it only takes 1.5 seconds instead of 2.5 seconds. Yeah, this might feel or seem a little bit artificial at this point. The very last one of these examples, we'll start getting into actual IO calls with actually accessing the web or accessing a database, but it's just going to be the stuff to the right of the yield will change to be the appropriate function call. Any questions about that so far? Okay. Well, that leads us into the next PEP, PEP 380 from 2009. And this PEP is the first one that's directly inspired by the need for multitasking in Python. So 2009, when people are first like really doing multitasking in Python with coroutines. And the idea is that, so it'd be very common for us, okay, we have I don't know, these two operations like get page and read DB. Very common for us to want to make a worker process that's able to do both of these two things. But if we just create our function like this is not going to work with our scheduler, because remember that these are coroutines, these are generators, and so these are yielding outputs. But the generator that this returns is just being totally discarded. We need this worker function to also be a coroutine. But this worker function is just a normal function, not a generator, because it doesn't have the yield keyword anywhere inside of it. And so there's this second version of the worker function, which, so here, again, get page, read DB, they're generators, so we can put them inside of for loops like this. And then this step is what get page yielded. And so we can then yield that step value. Whatever this function gave us, we will just give that back to the next function that called us. So just sort of like passing on that information. And then similarly with the readDB function, just whatever it gave us as the results, we'll just pass that on. And so now this worker function is a generator, and it will work with our scheduler function. It's a little bit annoying though to have to do all of this, like every time I want to do a function call inside one of these coroutines. And so this PEP 380 defined this new syntax yield from, which is if you have a generator on the right, it's going to turn your function into a generator, into a coroutine, and automatically yield all of those things. So this worker right here is, we can just do worker like that, and it's going to be able to call it with these two functions. And I could add more of those workers if I wanted, and it's going to interleave all of them, still taking essentially the same amount of time because it's really those IO operations which are now all happening concurrently, which are dominating the runtime. I don't know, this isn't like too much syntax to actually type out though. And so if this is all the syntax that you had to type out, maybe it wasn't worth like this whole new weird keyword right here, the yield from. But if we take a look at this link right here, we'll see that the actual syntactic sugar for yield from is quite a bit more complicated. So this PEP 380, this is the actual syntactic sugar for the yield from keywords. And if you recall that in a coroutine, we're not just taking information from the function, we're passing information to the function. And this for loop doesn't do any passing information to the function. It only gets the information from the function. So something like this handles both the getting the information from and passing it to. So it's more complicated than is worth us going into detail. But that's, yeah, that's what the yield from is. Sort of a bidirectional link between these sub-coroutines and the outer one. At this point in Python history, people were using these coroutines pretty regularly, writing lots of cool libraries to make asynchronous code and things go much faster. But there's still a problem in that when I look at like just a function like this, because it's still just using the def keyword right here, because that's what Guido decided we had to use for generators back in 2001. It's really hard for programmers to realize that this is supposed to be like an asynchronous function doing asynchronous things and keeping that separate from our synchronous functions. We can't just, one of the weird things about these async functions is we can't just call them directly. I can't just call like readDB like this. That returns this generator object that I have to do something with. I have to yield all the values from. So really every time I'm calling one of these asynchronous functions, I have to somehow put it in one of these schedulers in order to make it work. I have to do scheduler of readDB like this if I actually want to read from the database. And it's not obvious that that's the case just looking at the function definition here. So 2015, PEP 492 adds this async keyword, modifying the definition right here. At this point, Guido is still the BFDL for life, but he admits he made a mistake, and the function definition for these coroutines should look different. And so this is the syntax that they decided on. And if we come back over here, just so we can compare the two, what's changing here in all these function calls is the def is changing to a async def. And then every time where we had the yield before, used to yield this complicated sort of expression. Now it's just await and then the name of a function or the result of a function. So we just await the sleep call. Anytime we want to call one of these async functions, we have to await the result of that async call, which under the hood is just doing a yield. But then we can do a normal return down here at the end. And so this syntax right here looks a lot more similar to this original motivating multitasking syntax. Doesn't have these weird yields all over the place. We still get to keep the return at the end. We just have to put async in front and async in front of all our function calls. So I'm going to close this one that's in the middle, so we can go back and forth. The only difference here between the naive sequential thing and the thing that we actually want that's going to be asynchronous, put async in front of the def keyword and await in front of all your function calls. Under the hood, let's see, so the read DB, exactly the same. Now these workers, it's an entirely symmetric deal here that it's still just async in front of the definition, and then you await all the function calls just like we awaited the function calls up here. Actually creating the functions that do the IO now though is relatively complicated. We have to introduce this await dunder method, which is like the equivalent of so underscore await, or any object with underscore wait is called an awaitable object in Python. The async syntactic sugar makes this function be awaitable for us automatically. But this await function, the await function plays the same role as the iter function in generators. And they turn out to be basically exactly the same thing. Vast majority of built-in Python awaitable objects or generators just define await and iter to be equal to each other. And here you can see that await is a generator object right here, yielding these things that we were previously yielding manually before of whatever our IO operation is, and then the delay that we want to wait before checking whether that operation has returned or not. Down here, this function sleep does not have the async in front of it, but it is returning this awaitable class, and so that makes this sleep also asynchronous and something that we can await up here in our asynchronous functions. So there's a number of these tutorial references that I have right here, like these ones here, and then we're going to be starting to go into like the actual practical things, how to use these libraries next to do asynchronous operations. And at least for me, having this sort of knowledge that everything under the hood is really just a generator, really just an iterable, helps me sort of understand the potentially really weird error messages that you're going to get out of things. Let's see, so this is the 0.5 Python now. 0.5. And we can just rerun these exact same scheduler functions that we were running before. Same exact scheduler function. If we come down here to the bottom of this file, It's actually just importing the scheduler function from the previous file. So the scheduler is exactly the same. The only difference between these functions is really that we're using this async syntactic sugar now to replace all of those yields with await and return. And again, if I were to call read db by itself, now it's telling me that I have this coroutine object. Anything defined with an async is going to give me a coroutine when I run it. And this coroutine is something that I have to put inside of one of these schedulers in order to actually get it to work. Scheduler, read db, and now it actually works. Okay, so that's from a debugging purpose, that's the main thing to take away, is that if you're calling a function and you're getting something that looks like this, it says coroutine or generator, then you know that it has to be put inside one of these scheduler functions in order to make it actually run. The scheduler that I wrote out manually over in the previous file is a little bit naive. The actual recommended one to use with Python is significantly more complicated. So we won't talk about the details of how it's implemented, but it's provided for us in this Async Io library. As of 2015, PEP 492, this fully standardized the syntax for asynchronous functions in Python, and the syntax is guaranteed never to change in the future now. I don't have it written here, but this is Python version 3.5 is what corresponds to this PEP. This PEP made it into version 3.5. Lambda server has version 3.6 on it, so yeah, I have access to all these async functions. The syntax of async functions never going to change in Python, but the sort of standard libraries and the user space libraries that people are creating, those do still continue to change with all the newer Python versions. So this Async Io is the standard library for working with async functions in Python. Again, the async functions just being coroutines, coroutines just being generators, and generators just being the classes that implement the iter in the next under methods. But one of the main things that Async Io provides for us is one of these schedulers. And so this, this function right here, get page, I've just here, that to the right, yeah. So now you can see that the get page functions, the read db functions defined exactly the same in our previous syntactic sugar async file and our 06 async io.py file. No difference at all between these functions. The sleep function, though, is coming from Async Io. It's going to actually do some IO operations for us. The previous sleep function, again, defined in this sleep class, which just had this sort of dummy await function inside of it. But this sleep actually will do the proper IO. And then inside of, let's see, let's actually open the file now. This, in order to actually use any of the libraries or any of the things inside of Async Io, we have to create one of these scheduler objects. And the standard terminology for these scheduling objects is called an event loop. So we say something like loop equals, first I got to import Async Io. Loop equals Async Io dot new event loop, like that. And now this loop function or this loop object will have a function called run until completion. And run until completion, I can pass in something like get page, like that. And let's see, do I have a typo here? Run until complete. Get page, like that, and it's actually going to run it and do whatever IO is necessary to be done. here I just did the individual get page. I could change this to being a one of the workers, so worker like that, and that's going to do both the get page and the read DB. Line 22, that read should be read DB like that. Little typo there. Should be calling this function right there. Close that, do that. Import Async Io, redefine the loop equals, and then loop.run into complete worker, and there it ran both of those two objects. One of the weird things about this run until complete, or the difference from that scheduler function that I had before, is that the run until complete only takes exactly one function at a time. And so if you wanted to like run multiple functions, you might be tempted to do something like first run this one, and then run this one, and then that'll run two different workers. But if you do that, then you're not going to they're not going to be run concurrently at all. It'll be this run until complete is an ordinary Python function. It'll be a sequential function, and so anytime you have something that looks like this, it's going to not be able to run concurrently. If you wanted multiple workers to run at the same time, there's inside of the Async Io library. So if I do Async Io, there's a function called gather, and gather will take multiple different, say like two workers like that, and put them together into a single object that's called a future, which will run both of these together. If I take that and run the loop.run until complete, and we look closely, yes, so this is the tricky part about these async functions is you get weird error messages that aren't particularly helpful in getting you to debug what they are. And this one is, I'm not able to see what my typo is right now. So we will pause that for a second and go on to the next real world example that does actual I/O reading from a web page, and then I think that'll help us out here as well. Up here, if I open up the 7 AIO HTTP, this file comes from the AIO HTTP library documentation. It is a, so this library is not built into Python. It's, you have to pip install it. And so we've seen that like the built-in libraries changing a lot, built-in Python stuff changing a lot in the last few years. The user space library is changing even more rapidly. But AIO HTTP is what people have sort of settled on as the sort of the what's the most common library for accessing web pages. And in their documentation, they have this client example right here. So this client example is what I have in this file right here. Importing AIO HTTP, Async Io. And you can see there's a bunch of these different async calls throughout here to make stuff work, and then some awaits as well. And so the way that we should be thinking about this, again, is always find what our event loop is. So down here at the bottom, this loop variable, getting the event loop right here. And then we're running until complete, just a single, just one function, just this one main function. And yeah, so running this one main function by itself. Here, the with keyword has async with it, because if you recall what with does is it runs this function right here and stores the results in this variable right here. Because it is calling a function and it is inside an async function, it has to await the result of this call. This function right here is also defined as async. And so the async with will await this before putting it inside here. Similarly, this async with will await this before putting it inside the response. And then the response will give us a status and the headers. And it turns out you have to do actually even more IO operations to get the text of the web page. And so you have to await that as well. So there's 3 different awaits, 3 different function calls inside of here. And then at the end, it'll print out the contents of the python.org webpage. So let's go ahead and run that. And there's the contents of the python.org webpage, or the header up here, and then the first 15 bytes of the body. Where we're going with this for the homework assignment is, so it's divided into 2 parts. The first part is stuff that we've totally covered in class today, and that is it's a sort of a review assignment for people who've taken CS46 with me. Those of you who haven't, though, you'll have to complete this assignment. And the idea is there's this containers repo. Inside of the containers repo, there's these 2 files, Fibonacci and range, and both of these are generators. And you'll have to implement generators in both of these files. So up here in the Fibonacci file, it has some inefficient definitions of the Fibonacci function. Inefficient because they're going to be using O of in memory. And so down here, it's getting you some practice using the yield keyword and the more verbose definitions of iterators, so that you can get comfortable with that before starting in on the actual coroutine part of the assignment. Down here, the range function is asking you to re-implement the range function in Python using a generator. And then, yeah, same as all the other assignments, if you get those implemented right, then these test cases down here will pass. Submit your repo to GitHub, and you'll get the credit. And again, this first assignment right here is only for only people who didn't take data structures with me need to complete it. Last class, Wednesday, we'll be talking about the second part of this assignment, what you need to do for it. We're going to be extending this this type of downloading right here. Instead of just downloading one web page, you'll scan a chunk of the internet and download all of those web pages on that chunk of the internet. And you'll be doing that in this concurrent asynchronous fashion, so that it'll just happen in a couple of seconds. But you'll also do it sequentially, and you'll see that it'll take a couple of hours to do it sequentially. So go from hours down to seconds using this this async technique like this. Any questions? Okay, then we'll stop here for today a little bit early and pick up with this on Wednesday with the assignments.